Check this out. This is a multimeter. I promise that I will make you better at using one of these than most of the techs in a dealership. Let's get to it. So this is a relatively basic, straightforward, automatic ranging multimeter made by Fluke. This is a really, really nice one. They've got really complex units like this one here that have all kinds of little features, and they've even got these lovely little doors to make sure that you don't stick it in the wrong hole. You don't need all of that. All you really need is a decent quality, well-built meter. This one is from Klein Tools. There's no sponsorships to any of these meters here, so I'm just telling you what I think. This is a manual ranging meter. A little bit more difficult to use just from the perspective of you need to tell it what you want before it'll give you your readings, but it is more than good enough. I've been doing this for about 20 years, and this is the meter that I carry around with me the vast majority of the time. If it's good enough for me, it's good enough for you. So what's our first step? We're gonna look at voltage, amperage, and resistance. Those are the primary things that you're gonna do with a multimeter. Continuity is also a very good one, which kind of falls under the resistance category. So step one, check your meter. Make sure that it works. We're gonna go, and I'm gonna break all these down, but the first thing we're gonna do, let's hop over to the continuity setting, and we're gonna test our leads, make sure that these things are good. Because you know, I've seen it a few times where somebody's chasing something for hours. Well, guess what? Turns out there is just a bad lead. We're set to continuity, touch your leads together. You should get a beep. Wonderful. Okay, that means our leads are good and our meter is good. What's next? Leave it in continuity, and then we are going to, there's 3 little ports on the bottom. We have amperage, we have our common port, which is for our ground, and then in this one, we have milliamps, microamps, volts, ohms, diodes, and continuity. Every meter is a little bit different. See, this one right here still only has 3 ports. This one right here has 4. Our milliamp port is right there. For automotive use, the vast majority of the time, our 10 amp port is the one that we are going to be using. Go over to continuity. My meter beeps, tells me that my red lead here is good. When I stick it in the amperage, oh, look at that, I must have replaced the fuse in that one. Huh, how about that? If I'd had a blown fuse, you wouldn't get anything. The purpose of that fuse is to protect the meter, because when you're in our amperage setting, our meter essentially works like a piece of wire. What happens if you were to take a wire and connect it directly to the positive and the negative on your battery? Poof! Gone. Not great when that happens to your meter. Another nifty little tool that I made is a inline fuse holder. This is just micro fuse holder out of any car. And I took a couple of banana connectors, because that's what these ports are. They're banana connectors. And then I can stick this right in there, and then stick the other end to my lead. Why is that useful? Why not just use the internal fuse? Well, internally, these are fused to 10 amps. I have this little guy set up at 7.5 amps. So if I'm doing something that might be a little bit risky, I'm gonna pop that fuse instead of the fuse in here, and I don't have to take my meter apart to replace this. I've also had situations where I have a vehicle with an automatic circuit breaker in it. So what is a circuit breaker? Circuit breaker is like a fuse. A fuse is a mechanical protection device. It's an electromechanical device. Once the current in the circuit gets too high, the internals of the fuse will pop and open up to protect the circuit. Well, a circuit breaker is very similar, but it has a piece that will pop open, and then either manually you reset it, or some of them are automatic resetting. I had an old Corvette with a dead short in it. It had an automatic resetting circuit breaker in it. So what was happening? That circuit breaker was opening, closing, opening, closing, opening, closing. It was a dead short, but it only showed up as a 1 amp draw. So when I hooked this baby to it, she popped the fuse. And that's what inspired me to make this, so that it would pop this fuse instead of me having to pull my meter apart. And they're not terribly difficult. This one has 1 screw there, this pops out, and then there's 4 screws around the edges. This one very similar, and then this cover comes off, and this one has just a few more screws on it. But yeah, they're all a little bit different, but they all work basically the same way, except for your super El Cheapos that you buy off of Temu that are unfused for like $9, but in that case it's cheaper than the fuse, so I guess, you know, do with that information what you will. What's next? Your choice in leads is important. These ones are the name brand Fluke leads. They came with my Fluke meter. They work well. They've been around. I've had this thing for like 15, 20 years. Awesome. However, there are some limitations to these in that they only have these little probes on them. This is a fairly basic, I think this was about 30, 40 bucks. I bought off of Amazon. They get the job done, but what's really cool about these is you can change out the leads. So what might you want to change them to? Well, for the ground specifically, I like to put an alligator clip on there. And then that way I can go right to the battery, or right to wherever my ground is, and I keep it there. So I know that I always have a good ground. you don't want to be taking your leads here, and every time you're testing, you're moving, you don't know if your ground is going to be good or bad, right? Like I've seen that happen. Usually it's good, sometimes it's not. There's also these smaller little alligator clips, really, really useful and handy. And check these out, back probes that go right onto your leads. What is a back probe useful for? Check this out. This is a knock sensor. And if we wanted to, obviously this one has been cut out of the harness. If we were still on the vehicle and we wanted to test this, we could take our back probes. We could use a wiring diagram and figure out which is power, which is ground, go directly to the power, and then take this and stick it on the ground. Or we could go both wires directly on the sensor itself. And then it's as simple as that. We are going between, there's a little rubber weather seal inside of there. And then we are just going between the wire and that weather seal. Now, a lot of manufacturers do not recommend this method. They recommend using a breakout box, which is awesome if you have it. Never had the opportunity to use one of those other than for the basic OBD2 port testing. So back probes is the way that I like to go. Really don't like poking wires. Let's test this knock sensor. I know that a knock sensor is going to produce a voltage form. I am going to go, it's a relatively low voltage. So let's start at 2. If you have an auto ranging multimeter like this one, all you have to do is set it to voltage. Make sure that we're in DC volts, because automotive systems other than the alternator use a battery for your electronics, and a battery is a DC voltage source. What does that mean? Electrons flow in one direction. So let's hook this up. I'm set to 2, and then if I give this sensor a light little tappity tap tap, you'll see that it's generating a voltage. That's pretty cool. Now, generally, anytime you set your meter to voltage, I recommend checking it on the battery. We checked our leads with the resistance test, and I'm going to tell you in a minute why resistance tests always aren't the most reliable thing. But anytime I set up my meter, I always like to check it on the battery just to make sure that, hey, we're good. Plus, the other thing that this tells us is, do we have a charged up battery? What should a charged battery be? Normal voltage on a fully charged lead acid battery or an AGM battery that you'll typically find in an automotive situation is approximately 12.6 to 12.7. Battery has 6 cells. You have 2.1 volts per cell. This is a lithium iron phosphate battery out of a kayak, and they have a slightly different fully charged resting voltage, but we're expecting somewhere around that 13.3-ish, 13.2, 13.4 on one of these, 12.6 to 12.7 on a lead acid AGM battery for automotive purposes. That's voltages as simple as that. Cool, so we found our voltages. On this meter here, obviously for a 12 volt battery, we need to set our meter to 20 volts. So we would go whatever the lowest setting is above the voltage we're expecting. So if I'm gonna inspect a wall outlet, I would go over to, I'd have to be on AC, alternating current, voltage, and 200, because here in Canada, where I'm located in North America, we are expecting to see 120 volts or 110 volts out of our wall outlet. So 20 volts here, and if we had it set wrong, no worries, it's just going to give us an OL for overloaded. And if we were to set it too high, we're still going to get our voltage, but it is going to be much less precise. See here, when I'm set to 600 volts, I'm getting a reading of 13. Still giving me a reading, but not nearly as precise as 13.37. And let's go over to resistance next, because that's a really good point on these manual ranging multimeters. So my resistances are over here, and when testing my leads with each other, I'm going to go on my lowest possible resistance. So I can either go continuity or, on this particular meter, 2K. And I should get darn near close to 0. Now, real world, there's a slight amount of resistance in just about everything. Let's just swap these leads out here. Okay, and let's take a look at that precision that I was talking about. So here we have 0.000. Great. If I were to go to 20K, it's still going to give me a reading. Notice I only have 2 decimal places. 200K, 1 decimal place. 2 million, well, it's giving me 3 decimal places, but let's grab something. Let's grab an actual resistor. Here's a circuit. I have a resistor here. I have a resistor here. You can't have the circuit live. How does a multimeter read resistance? Your meter is going to send out a very, very small amount of voltage. Let's find out how much. Let's see here. Let's check our voltage and our current. So for voltage, I'm going to set this meter to voltage. This one is set to resistance, and I'm just going to plug that in there. Look at that. We are under 1 volt. Just over a volt. We're hovering around a volt as I change through, as I change through the different settings on this manual ranging meter. So what does that mean? When you have a system with a 12-volt battery, it is going to beat the meter every single time. You're not going to be able to get an accurate resistance reading because 12 volts, 1. Now, I did say we would check the amperage, and since I've actually fixed the fuse on this, let us do that. I'm going to set this over to my DC amps. And look at that. We are not even registering an amperage. Being sent out of this meter. Cool. And what is amperage? Amperage is electron flow. So there's not a load in this meter, which is probably why we're not registering an amperage there. And you know what? This is confusing science. Relatively difficult to figure out how to do this without blowing anything up. So we're just going to move on. This isn't pertinent to what we're trying to figure out. So what do we need to remember here? What we need to know from this, when we're measuring our resistance, the meter sends out a very low voltage, and that voltage is going to get overridden by the higher voltage of your battery or your system every single time. So when we're measuring resistance, our circuit has to be dead. It cannot be live. So what do I have for resistance? My circuit is dead, and I am showing on my manual ranging meter, I'm set to 2 million, not showing any resistance. As I bring it down, now I'm going to get a reading. And that reading gets more and more precise until I hit overload, as I have flipped through my different resistance readings. So my reading most accurate came at 2K. So what does that mean? I have 0, there should be a 0 right there, 0.465 kiloohms. So if we were to get rid of that 0, do a little bit of math, we would have 466 ohms, just under 500 ohms, because that's approximately 0.4, it's about half of a kiloohm. Hold on a second here now. I said there were a few things that we needed to keep in mind for resistance. I only told you one. The other thing that we have to keep in mind, the resistor has to be disconnected from the circuit. Because what do I have here? I have a series parallel circuit. Parts of the circuit are in series, parts of the circuit are in parallel. So if I was measuring part of the circuit that was in parallel, in a parallel circuit, the total circuit resistance is going to be equal to or less than the lowest resistance in the circuit. So if I wanted to get an accurate reading on my resistor, I would need to disconnect it from the circuit, and now I could take a reading. And notice, if I were to read the resistance of my body, I have a resistance. There is an internal resistance, and we're all going to be a little bit different depending on how sweaty we are. So you don't want to just hold the piece in your hands while you're taking a reading, although in theory, total resistance of a parallel circuit is equal to or less than the value of the lowest resistance, so I should get a pretty accurate reading on this, but the better way to do it would be to use alligator clips. And it would be superbly helpful if I had 2 small ones. Okay, so here we go. Now I have my resistor and my alligator clips, and I am just going to turn down the resistance of my meter until I get a resistance value. And this is just about the same as what it was in the circuit, so that particular resistor was fine. But depending on what kind of circuit you're working on, that may or may not be the case. So let's put this into a real-world automotive application. I have an ignition coil. Woo-wee! Go me. This is out of a 1994 Lexus SC400. And when you are testing coils, it's pretty common practice to use resistance. Your primary coil, so this would be our primary side, you would have somewhere between 1 to 3 ohms, although sometimes you get less than 1 and it's totally okay. And then on the secondary, which would go from your ground to the output, the high voltage portion of the coil, you're going to have somewhere typically between 6,000 to 30,000 ohms. So let's test this. Set to 2,000, and I'm going to test my primary side of the coil. Wow, look at that. That's showing 0 kiloohms. And if I put it into continuity there, I'm showing half of an ohm. So what did I say? 1 to 3, sometimes less than 1, half an ohm, that's less than 1. Okay, we're good. Now, we got to check our secondary side, which is going to be What did I say there? 6 to 30,000. So let's set this to 200,000 and let's check. So this is showing me 18.2 thousand, 18.2 kiloohms. If I set this to 20,000, you'll see that it's 18.19, so I'd have 18,190 ohms. This coil's good, right? If this coil was good, why would I have it on my bench? This coil is no good. And that's why I don't like resistance tests. Did you see how low of a voltage the multimeter sent out? It was only 1 volt. What does this operate at? This operates at system voltage, which is about 14.5 volts on this vehicle when the alternator is running, and a primary side of a coil when the magnetic field. So how does an ignition coil work? You build up a magnetic field, it collapses, and then it induces spark. Magnetism, science. Science is expensive. So when that magnetic field collapses, you can get voltages, not on this particular car, but on some high performance vehicles, up to 100,000 volts off of your secondary side, your high voltage side, and up to 400 volts on your primary side. So is 1 volt going to accurately test something that can handle 400 volts? No, it's not. That's why I like testing your amperage or your voltage drop, because it's a dynamic test. It's testing the vehicle or the component while it's in use. Allow me to demonstrate. Okay, check this out. We're going to use a spark tester, and that's going to take the place of our spark plug. And then this goes back to ground. I've got a little tiny fuse in here. These are just some wire leads. Before I connect my fuse, I'm going to prove to you that these wire leads work. Yeah, buddy. Visual inspection on that fuse, it's still complete. So I'm set to just small engine, like 10,000-ish volts is all that it would take to turn that thing on. And then as I do this, create, you can see a tiny little spark down here, so something's happening. That means, I believe, I want to say that the primary coil is working, but where did my spark go? Yeah, there's no spark out of here. So what does that tell us? That tells us that resistance tests can't always be trusted. So if it fails a resistance test, it's bad. But if it passes one, it doesn't mean that it's good. So where might a resistance test make sense? Well, so here I have a temperature sensor, and I am going to hook up just to the back pins there. There we go, those aren't crossed. Although you can do this with a voltage drop test on a vehicle, so that would be the way that I would recommend going. So here we have temp sensor, right? I've hooked this up to resistance. How does a temperature sensor on a vehicle work? They are an NTC type, negative temperature coefficient. What the heck does that mean? Them is a bunch of big fancy book learning words. What that means is as the temperature goes up, the resistance goes down, which is quite the opposite of normal. If I were to just take this wire and set it on fire, the resistance is going to go up as the heat goes up. So let's try this. Let's warm this up. And look at that resistance just plummet like my investments. And then it'll eventually hit where the bottom of this sensor is designed, and then as it cools down, that resistance level is going to go back up. So the other way that we could do this is, I talked about voltage drop. Let's set that up. Okay, so here is my simulated temp sensor circuit. I have my wiring, I have my temp sensor, I have a resistor, and then I have my power source. Why do I need a resistor here? Well, inside a car, you have a module, and that module is going to read voltage right here. Why? Because it knows that there is 13.3 volts for the system in this particular case, and the voltage here is going to change based on this resistance. So I have my multimeter set to 20 volts. We're going to follow my own advice. We are going to use an alligator clip here to go to ground, and I'm going to check my system voltage, which is 13.3. On the other end of the first resistor, and as remember, this resistor is going to use up some voltage. It's going to consume some voltage. I have 13.08. So I had a high resistance here, low resistance here, so I'm only consuming a little bit less than 0.3 of a volt. Okay, that kind of makes sense. Let's put my test lead right there. Come on, get in there, make this happen. And check this out. As I heat up my temp sensor here, woo, warm, warm, warm. The voltage is going to change. Why is that? Because the resistance is changing. Check that out. Look at that drop. Again, like my stocks. So that is pretty cool. Why is this test more accurate than the resistance test that we did? Because the numbers are a little bit different, but it's basically the same thing. A number changed, did it not? Yes, it did. This is a dynamic test. This is a test with the system loaded. No matter how small that load is, it is still loaded, and this is how the vehicle is going to monitor the system. If we had a bad sensor right here, say an open circuit, check out what happens to our voltage here. Skyrockets up. You would get a code for circuit voltage high. Faulty sensor. It can be either a faulty wire or a faulty sensor, but in this case, we're just pretending we have a faulty sensor here. So that's why I much prefer to do the voltage drop test compared to just a resistance test. It's dynamic, checks the vehicle the same way the vehicle checks itself. Love that. However, where is a resistance test useful? Where a resistance test becomes particularly useful would be in a scenario like this. We have a piece of wire, and let's say that it's wrapped hard around part of the frame, or maybe the engine block. Well, if that is not insulated properly, there is going to be, as the vehicle operates, runs down the road, the engine moves, there's going to be some rubbing going on. And it is possible that a piece of wire, so it is possible that through that chafing, we may get one very small, tiny little piece of wire that's connecting our chassis ground. I've simulated that with this back probe here. Where the resistance tests are useful is if we were to go from that wire, wherever, so this would essentially be like a connector, like this piece right here, we could back probe in there, and then if we were to take the other end here and attach it to chassis ground, because that one tiny little strand of wire is touching the engine block, well, if we were to load the circuit like I had just taught you to do, that little piece of wire, it can't handle all of the amperage of a loaded circuit, so it's not going to affect the operation of the circuit while it is loaded, especially if we were to use something like, you know, a test light or a light bulb to load a circuit, test a wire, because that's a great test. However, that might throw off a very voltage sensitive module. So here, having our resistance test, because it only sends out a very tiny amount of voltage, would be fantastic, especially our continuity test. We're connected to our sensor, our wire, that's not supposed to be connected to ground. You connect your other end of your, you connect the other end of your meter, the other lead, to the ground, and it can pick up even the tiniest little single strand that has chafed through a wire and is making contact with ground. So that's the one time your continuity test or your ground test is like, yes, that is the test that I want to go to and I want to use. Now, I made you one more promise, amperage. So for the amperage, we are going to set it to 10 amps. All of the lower settings are, you know what, they're much more useful when you're building circuitry and you're trying to find like milliamperages, or possibly you might go into the milliamp setting if you're trying to look for a small parasitic draw. Usually something that is 30 milliamps or higher, slightly different on every vehicle. I wanted to use this light bulb, but this one's a little more practical for this demonstration. Light bulb on. For our amperage demo, we are going to measure the amperage of this light bulb. So our circuit is live here. In order to check the amperage, we have to set our dial to amperage, and this is DC, so I'm in DC amps. You take your red lead out of the voltage port and stick it in the amperage port. Really important here, disconnect the circuit, and then hook your multimeter up in series with the circuit. And then the circuit should reactivate if your fuse in here is good. And remember, at the beginning of the video, I showed you how to check your fuse. So here we go. We have a 0.26, 260 milliamps draw, which makes sense out of one of those little light bulbs. If we had a larger bulb, such as one of these fog light bulbs, you would have a larger amperage draw. Power, ground, don't touch those together. Bigger, brighter bulb. Disconnect my circuit, connect the multimeter in series, and you'll see that I have 3.47 amps. And notice that there's a negative there. I just had the polarity reversed. I had the power and the ground reversed from my meter. Not a big deal. Ignore that little negative sign. It's not like I hooked the light bulb up and instead of giving light out, it's sucking the light in and creating a black hole. There you have it. Now you know probably better than about 90% of the techs that are out there working on cars right now how to use your meter to its fullest of potential. And you're not going to get bit by a resistance test that's gone wrong. So, what other tricks do you have for your meter that I may not have covered here that I should cover in an advanced meter use video? Let me know in the comments. Thanks for watching.